Hello, everybody. Thank you so much for joining us. I'd love to be there in person. It's not quite the same, but, well, this is what it is at the moment. And let's hope we have some fun over the next few minutes. Going to do a bit of talking about what metrology is, and then I'll explain to you a little bit about measurement, which is what metrology is. And then we'll go on a lab tour. We'll go and look around some of the labs at NPL. Hannah helped shoot some videos of that, and then we'll take some questions right at the end. So the first thing is metrology. Today is International Metrology Day, and I have to tell you that nobody knows what metrology is, or very few people. So I need to tell you right off that it's not meteorology. It's nothing to do with the weather, and it's nothing to do with meteors. Although I can tell you that in order to predict the weather, the people who do the weather service here in the UK do 125 million measurements every day in order to be able to predict the weather. Anyway, so metrology is about measurement. It's the science of measurement, and meteorology is the science of the weather. So let me now dig a little bit deeper and explain what measurement is. It's all about comparing something you don't know against something that you do know. Right, so you do know the length of a ruler. It's got it written on the side. There are all these marks. But do you trust those marks? Do you trust that they're right? So actually you have to trust the length of the ruler. And if I had this remarkably large chicken and I really wanted to know the height of this chicken, how do I know it's large? Because that's the size of my car. If I want to know the height of that chicken, I'd get my ruler and I'd measure its height. But I'd have to trust that the markings on that ruler are what they say they are. And then also, to make life more complicated, I guess the ruler might be jiggling a bit. If I'm standing on the card to measure the chicken like that, and the chicken might be. So how we do the measurement also affects the result. And we end up with an uncertainty in the result. We're never quite 100% sure that the result we're getting is absolutely what it is. Now, I don't know if you saw the advert, you probably didn't, but the advert for this talk had a teaspoon on it. And those people who saw that might be thinking, what has a teaspoon got to do with measurement? Oh, a load, absolute load. All teaspoons are not the same. These are some, not all, some of the teaspoons from my teaspoon drawer. I've got 27 different teaspoons. There's only a couple that are the same. I don't know how this happened. Anyway, is your teaspoon drawer like this? They're all different. And does it matter that they're all different? And by different, I mean when you spoon something out, you get different quantities out of them. If you're doing cookery and you've got, it says teaspoons of this and teaspoons of that, it probably doesn't matter too much. But there are some cases where measurement of whatever it is with a teaspoon is important. For example, medicine, if you're dishing out medicines. And there was a report from the National Health Service in the 1980s that complained that a teaspoon could be 2.5 millilitres, or it could be 7.3 millilitres. That's an enormous range. That's a 3-to-1 difference. And you could imagine getting 3 times as much medicine as you ought to if someone really messed up on how they defined the medicine taking sort of stuff. So as a result of this, nowadays you tend to get a special teaspoon that comes with the medicine in the packet, and it's worth spending that little extra bit of money just to make sure that people are getting the right amount. Now, I don't know if you heard the phrase born with a silver teaspoon in your mouth. Luckily it doesn't actually happen, but it means that some people are really privileged. So you can imagine a really privileged family who've got just loads of stuff, and here's their giant teaspoon. And then you can imagine a not so well off family with their tiny little teaspoon. The have-nots get quite envious of the haves in this sort of situation, and this quite often leads to a revolt in a revolution in a country. And this did happen in England in about 800 years ago. They rebelled against the king because the king seemed to be above the law, and so they forced him to sign this charter that effectively said, I'm going to obey the laws like everybody else does. So the Magna Carta, this document, was signed by King John in 1215. And it's really interesting to me as a measurement scientist to know that in there that are the definitions of a single set of measurements. It says that there is to be one measure of wine and ale and corn. These are the things that are important to them within the realm. And then actually said which measurement unit is supposed to be used, something called the London quarter, and we're going to measure cloth in a particular way, and we're going to measure weight in a particular way. So from 1215, the United Kingdom has had this sort of statutory thing that says you must measure things in this particular way. And they had these measures. A little bit earlier, there was a guy, Henry the First, and he had a sort of a definition of distance. It was called the yard. It was called the King's Yard, and it was the distance between his nose and his outstretched and the thumb of his outstretched arm. And you might think, what a ridiculous unit of length. What has that to do with anything? It's to do with cloth, because when you're measuring cloth, you kind of hold it to your nose and then you outstretch the long piece of cloth, and the distance between those two is kind of a nice measurement of length. So yeah, that's the King's Yard. Of course, it was just Henry I's physique that decided what the size of this yard should be, and later on people did it differently. We had the Elizabethan yard. She did exactly the same thing, and you can imagine her posing for a portrait like this. Well, she also sort of posed for the yard, and so they had this piece of metal that had these two scratches on it that Queen Elizabeth helped make in 1533, and it lasted for 300 years. For 300 years we were using this unit of measurement to measure length, until it was destroyed when the Houses of Parliament burnt down in 1834. Nothing to do with Guy Fawkes. That was late. This happened after that. Yeah. So one of the problems of having a measurement unit like that and relying on just one thing is that it can get destroyed or tampered with. Now, the French, everything I've said so far is about the English. The French did not have anything like this, and so they had a revolution as well. And at the point of their revolution in 1790s, somebody did a count, and they had 250,000 different ways of measuring length and mass, which is just crazy. So if you went to get a centimetre of something from one place, you'd get a different length of stuff to if you got it from somewhere else. And you can imagine how that would really prove a problem if you were making something, or just unfair if you were trying to buy something. So part of their revolution involved setting up this single system. Everybody would use the same set of measurement units, and they had the foresight to ask if other countries would join in, because that way you could trade with other countries. You could sell stuff and buy stuff from other countries, and engineering would work between the two, because you know you were buying bits that would fit together. So they asked the United States of America and the UK to join at this time. Both these countries said nothing. They didn't join in. So at that point, that was it. France had its own set of units, which worked very nicely, thank you. They revisited this idea of having an international system in 1875. And on this day, 20th of May in 1875, they had this convention. It was actually a scientific convention, but it was also a political one. Lots of leaders turned up to it, and they signed up and agreed that from now on, they would use this single set of units. And it was called the Treaty of the Meter. It set out how people were going to do measurements internationally. It said that a Frenchman would be involved. It said it would be based in France. This is the building that they built at that time to host all of the experiments and where they'd keep these length and mass standards. And here's a group of my colleagues hanging around outside. They've gone on a day trip to it. And that building is still there. And then they commissioned two bits of metal. One was to be the kilogram, just a single item that was the kilogram, and from then on everything would be referred to that one thing, a bit like the yard. And the meter, again, just one thing that was the meter. Now these things are actually, because they had better manufacture people in England, these were made in England and delivered in 1889. Hurrah! So today is the birthday of this international system of units. So thanks to that, at that time, we had the meter and the kilogram defined, and they had these things that everybody measures things against. So that trusting, do you remember the measuring the chicken? That trusting your meter is a meter is there. And since then, things have moved on a bit. We don't just have a kilogram and a meter, which I'm sure you've heard of. We have these other units. There are 7 now. The second for time, the Kelvin for temperature, the ampere for measuring electric current. So it's the electrical one, the mole, which you use in chemistry for measuring amounts of substance, and the candela, which is appropriate for this one because that measures how bright light sources are, and it's based on candle power. So these are the 7 base units of measurement, and you'll have these in physics and biology a bit, and chemistry a bit too. So the world is big, but if you wanted to get one of these, you'd need the bits from all over the place. And so everybody here has to agree on what a millimetre or less than a millimetre is. So it's really, really useful that we've got this international system of units. And all over the world, we have these different languages. These are the different ways that you could say hello in all these different countries, but everybody uses this international system, it's called the SI, to measure things. So there are many ways to say hello, but there's only one way to properly measure length, and it's the international system of units. This is the slide we normally start our talks with. Welcome to NPL. This is the people that Hannah and I work for. This is the UK's National Measurement Institute, where we have our kilogram and metre and second and so on. We're based in Teddington near Hampton Court in London. We've got about 1,000 people working there, and we're funded and owned by the government, so we're government employees. And we've got about 400 different lab spaces. And let's have a look inside one of them. This is probably larger than your school hall. It looks like one of these torture chambers or some sort of big weird James Bond place. This is a laboratory. We do science experiments in here, and this lady here is setting up part of the experiment, and these guys over here are setting up another part. This is actually measuring how powerful this microwave transmitter is, but we use this for measuring how powerful radio antenna are, and you can use it for mobile phones as well. So you can't work at a place like we do, the UK's measurement place, and not have some funny stories. So here's a couple of projects that I was involved in. I measured the shininess of cats. Yeah, how shiny a cat is, because I was working on light measurement. Yeah, I had to build the machine completely from scratch, a cat shininess measuring machine. And then also we were involved in measuring the crispness of biscuits to see how different types of packaging affected biscuit wrapping. So the kilogram, here's the kilogram, which yeah, it's a litre of water, weighs a kilogram more or less. And in the old days, we'd have this thing called the kilogram. And now we have an electromagnet. I'm going to whiz through a load of slides now because I want to get to the lab tour bit, because we're running a little bit short of time. So let's go to the lab tour. Here we go. So, I mean, the main thing is everything can be measured against just 7 things. So if you want to make ice cream, you'd have the kilogram for the amount of stuff, interested in the size of the containers, time it takes to cook, electricity used to cook it or keep it stored. You measure the temperature, and the amount of ingredients is to do with the mole, and you need light to read the label. Right, so what do scientists look like? If I get to Google, I'd get all these images, lots of white lab coats. And I now want to show you what some real scientists really look like by lab tour. So here we go.
Radiotherapy is a treatment for cancer used within hospitals today. It uses beams of high energy but invisible light to kill diseased cancer cells within the body. Getting the power level right is really important, not too low and not too high. The science that measures this power is called Asymmetry, and my team helps with these measurements.
Hello, my name is Frankie, and I'm here to show you the 3D printing lab at NPL. Here, we can make any object you want from just plastic. I will show you how the 3D printer works, and then I will show you what I'm making. With this printer, the surface the object sits on, which we call the base, is dipped into liquid plastic. A laser draws the shape of the first layer onto the base. This makes the plastic harden into a solid. The base then lifts out of the pool of plastic so that extra liquid drips off and is dipped in again to add the next layer. Prints take a really long time, usually a whole day. When it has finished printing all the layers, I remove the parts from the base and wash it in a special chemical to remove any liquid plastic. Then I cook it in a special type of light called ultraviolet light. Next, we have to cut off all the special support structure. The reason why we need this support structure is because otherwise the print will turn into a big gloopy mess. After that, I sand it until it's smooth and then polish it. And glue all the pieces together. So here's my finished project. This is a phantom. The word phantom has a scientific meaning. It is an object which is exactly the same size and shape as a human body part, except it's made of plastic. But why am I making these plastic models? My colleague Warda will explain.
Hi, I'm Warda, and I'm a research scientist working on medical imaging here at NPL. We use these phantoms to teach fancy medical cameras here and in hospitals on how to take the best pictures of patients within the hospitals. Phantoms are cheaper, they're easier to use, and they're less gross than a human body.
This machine is the Spect, which is a special 3D camera. It is a bit like an X-ray camera used to take images in hospitals or of your teeth at the dentist's.
For our machine, the body part, or in this case the phantom, this is the phantom, this is a pelvis phantom, contains a special liquid in here called a marker that helps shows up the function of the body. These markers are dotted around this phantom, as you can see here, here, and behind here, which you can't see very well, but you will see in the image. This bone part is very similar to the bone of the human body. So when we scan it and we look at the images, it's very similar to what a patient would show up.
The camera head moves about to create an amazing 3D image. Here you can see an image of a phantom with the marker appearing inside it. This work can give doctors an amazing insight into how our bodies work and to help spot if there are problems.
Hi, I'm Mohammed and I'm a research scientist working on medical radiation dosimetry here at NPL. You've seen phantoms and the medical camera, but how do we know what the treatment will look like? We use a special computer program called the treatment planning software, such as the one you can see here. You can think of this as like a flight simulator for radiotherapy. The software looks at the images taken by the medical camera to see how the treatment will look and to help with improvements of the treatment. Here is what a real patient image looks like and what the treatment looks like. Areas marked red show the treatment concentrated on the cancer. Like a flight simulator, we can do lots of repeat simulations until we're happy with the treatment plan. The software can be used to tell the medical radiotherapy machine how to target the treatment, and you'll see the radiotherapy machine in a later video. Here is what a phantom image looks like. You can see how it looks quite similar to the patient image. We use these phantoms to check how well the software is at simulating the treatment. We use devices called detectors to take measurements in our phantom. You can see these here in the 3D rendering. So what you can see in orange and light blue are the detectors that we can embed into the phantom. And these measurements from the phantom allows us to check how good the simulation from the software was. My colleague Eliana will tell you more about how we do these measurements in practice later on. But how close are the images using phantoms to the images of patients? Over to my colleague Hannah, who will tell you more about this in more detail.
Hi, I'm Hannah, a postgraduate researcher working on medical radiation dosimetry at NPL. I do my research in the field of proton therapy, which is an advanced radiotherapy treatment. I spend my time doing lots of calculations and measurements with materials to work out if they can be used in phantoms for proton therapy. As Frankie previously mentioned, phantoms can replicate the shape of human body parts, but for these phantoms to be suitable for our work at NPL or in a hospital, the materials used for these phantoms must have very special properties. The materials used in building these phantoms should be tissue equivalent. But what does this mean? It means if radiation, such as X-rays, travel through a real bone, or our phantom bone, it will produce the same effects in both. But why is this important? If the phantom is made of materials that behave the same way as the human body parts, the phantom will look and interact with the radiation in the same way as the real thing. Images and measurements with the phantom give a good understanding of the science happening inside a real person. So here we do a measurement using a full body phantom, and the results are thought about by experts to develop their understanding. My colleague Ileana will now show you how we take scientific measurements with our phantom in a medical machine called a LINAC.
Hello, I am Ileana, and I am a research scientist working on medical radiation dosimetry here at NPL. This is a medical machine called LINAC. It's the same as hospitals used to treat adults and children with cancer. At NPL, we used it to test the effect of treatments in phantoms. This particular phantom, with the shape of a person's chest, is the one Mohammed was using. We cannot see them here, but inside the phantom are those devices called detectors that Mohammed also showed before. The phantom is placed on the couch where the patient will lie. Little markers make sure it is in the right place. The machine rotates around the body to distribute the treatment to the affected parts while protecting the healthy areas. In another room, treatment staff watch what is happening using cameras, and that way they control the process. Once we have delivered the treatment, the detectors are taken out and studied to evaluate how well the LINAC worked. All this work is very important and gives patients, radiographers, physicists and doctors the confidence that the treatments benefit the patients. Remember, it is all about measuring the right dose, exactly the same way medicines need to have the right amount of active ingredient, not too little and not too much.
Thank you very much. Right, so I'm going to stop sharing now, I think, and we've got just 1 minute maybe. If anyone wants to put any questions in the chat while we're waiting for those to come in, can I just say a little thank you, Hannah, for doing that. Oh, so Samantha has asked, what subjects did you take when you were at school? Hannah, what subjects did you take at school?
So I did for A-levels, it was mainly sciences for me, because I really enjoyed my sciences. So physics, chemistry and biology, and then maths as well, because maths is quite useful for science. But I did enjoy doing art and other subjects at GCSE too.
Fantastic. What's the best part of your job, asks Simon?
I think it is you know that you're helping people, so you're seeing the impact of your research is actually helping treat patients, and you're knowing you're giving people the best outcome in life. So that's what I enjoy. Yeah.
That's kind of what I feel about science generally, and I think, and there is a shortage of people doing STEM jobs in the UK, so there are loads of jobs waiting for you if you want to get into that. And
Andrew, I wondered if you could tell the student what's the best part of being a STEM ambassador and working with the young people.
Oh, giving something back. And nobody told me how useful science, technology, engineering and maths would be when I was at school. Well, they did, but when I was midway through my A-levels, and I wish somebody had told me that earlier. And then because I was going to become an artist, and I would have decided a lot earlier that science was the way to go for me, just because it helps people. And I think it's just a brilliant subject to talk about. It's wonderful, and it's creative as well. As an ex-artist, I realised that, you know, you start with nothing, and you build something that you're absolutely proud of. And with art, it's lovely, it hangs on a wall, but with science, you save people's lives. And the cancer work that you're working on, Hannah, is just remarkable. And you're working on new ways to do science as well, aren't you?
Yeah, exactly. So as I mentioned, proton therapy, which is really interesting because unlike X-rays, it doesn't pass all the way through the patient. So we can actually save a lot of healthy tissue and not irradiate it. And that's our goal, is to target the tumour, the cancer, but not radiate too much of the healthy tissue. So proton therapy really allows us to do that, and yeah, really enables us to help people more.
I just look at the machines like that Linac thing, enormous and massive, and I know a little bit about how it works, and it just is incredible. And things like that just make us feel like we're in the future. And like you look at Star Trek and Star Wars, and you just the technology they've got for medicine there is so much ahead of what we have now. And I just feel that you, Hannah, are part of that an amazing new journey into the future where people will live for 200 years, healthy and happy lives.
Somebody actually wants to know how much a piece of 3D printing like that machine would cost, Andrew. And they also wanted to know, which I think we'll ask Hannah, how long has she been doing her job?
3D printing, oh, it takes ages and ages. Just that thing that you saw in terms of the materials cost would be just a couple of less than £1 probably. The machines, the printers are about £2,000 each. The chemicals to do the washing and whatever, I mean, it's like cleaning fluid, so it's a couple of quid. But the main thing is the time. You have to design these things, you have to create them. They don't always come out right the first time, so you then have to redesign them. So no kidding, just Frankie's work in making these things, a lot of it is the design part of it, which again goes back to creativity and art. And then do you want to answer the other question, Hannah?
Yeah, of course. So I am still a student. So I am currently doing something called a PhD, which is a postgraduate research. So I've been doing my PhD for now 3 years. So I've been in the field of medical physics now for 4, because my master's the year before my PhD was also on this topic. So yeah, in total, I've been doing medical physics now for 4 years, but it still feels very new, and there's still so much to learn, and it's really, really interesting as a topic.
Thank you, Hannah. How do you know that your measurements are correct every time?
That's a good question. Lots of repeat measurements. We do a lot of checking of our measurements, and there's lots of people do a lot of I've spent a long time trying to understand the science so that we make sure that we understand any corrections. And you're saying we put uncertainties on our measurements, so we have to do a whole series of different measurements as part of our final measurement to make sure that it's correct.
Lovely. And one of the
getting the uncertainty as small as possible. That's our job, isn't it,
yes.
Hannah?
Yeah, exactly.
You know something, the closer you are to the truth. That's why I love science, because it's all about the truth. The closer you get to that, the better the world is. The more amazing engineering, the better medicine, the more accurate it is. It's great.
We're making an accurate teaspoon.
Yeah, teaspoons are rubbish. I think we're out of time, haven't we, chaps?
You have, and you've got a couple of questions that have come from particular year groups, so I'm going to forward those to you. So year 7B and year 8, do not worry, your questions will be answered, and therefore all I have to do is to say, Andrew, Hannah, thank you very much again for your time. Another very enjoyable and interesting insight into the world of STEM and research. Thank you very much. Thanks, and I know you have to go immediately because you've got primary children waiting.
They're waiting for us. Bye, everybody. Thank you so much for spending time with us. Bye.
Bye.